Hi, everyone. Today I'm going to cover the devastating earthquake that occurred in Venezuela on June 24th, 2026. I'm recording this video on July 3rd, 2026. I want to show you this surveillance footage that really brings the devastation up front and just it's shocking. You have these people running out of the building from an initial shock for the first earthquake, and you see this building across the street, multi-story residential building, just collapsing in an utter heap. And that seems to be a common story with the survivors. That there was about 39 seconds from the initial shock from the first earthquake that allowed more able-bodied younger people to flee their building if they were on lower stories. But the people who weren't as mobile or lived on higher floors or more interior to the building had no chance. So in today's video, I'm going to talk about what we know about the earthquake and, more importantly, what commonalities that the buildings that collapsed appear to have had in this instance, and then hopefully what can be learned in the future to rebuild in Venezuela to provide higher levels of seismic protection for the residents there. And I'm sure that there's lessons that can be applied worldwide to improve building safety in earthquake events. Well, you see this drone footage from the AP. This is just utter devastation. Blocks upon blocks of residential towers, multi-story residential buildings, had a pancake type collapse where the building fell in on itself. It's these types of buildings where most of the deaths occurred. As the date of the recording here, on July 3rd, 2026, they have reported over 3,000 deaths. That number is expected to go up considerably, considering that there's around 50,000 people still missing. The United States Geological Survey estimates that 30 to 50,000 deaths may have occurred from this earthquake. And that's a huge number to try and wrap your mind around. As a point of reference, 5 years ago, there was a building collapse, a residential building in Florida, Surfside condominium, that collapsed and killed 98 people. And in this situation in Venezuela, in the aftermath of the earthquake, you have literally hundreds, if not thousands, of these types of buildings that have collapsed on its occupants. So, this is the location of the earthquake just northwest of Caracas on the coastline. As I mentioned, there was an initial 7.2 earthquake that occurred on the Volcano Fault, which then triggered a rupture on the San Sebastian Fault. This is a strike slip fault, similar to the type of fault in California for the San Andreas Fault, where you have two plate boundaries moving horizontally or laterally one to the other. The depth of these earthquakes was on the order of 10 to 12 miles below the Earth's surface, which is considered to be a relatively shallow set of earthquakes, which can cause major devastation because of the attendant ground shaking. There's been some discussion whether there were actually two earthquakes or one 7.6 earthquake. But at any rate, the initial earthquake was a magnitude 7.2, followed by a magnitude 7.5 earthquake about 39 seconds later. This is the overall location, showing you the relation to the location of this earthquake to the rest of Venezuela. And you have a complex series of faults that produce these earthquakes. Most of the earthquake devastation from this Venezuela earthquake occurred along the coastal areas, in particular this town of La Guaira. And you can see that the geology of this area consists of mountain peaks, mostly metamorphic rocks, and then you have sediments deposited at the base of the mountains along the coastline, these alluvial deposits, these alluvial fans as they're called. And satellite analysis from the Sentinel-1 data from the European Space Agency shows widespread damage. Not as much damage in Caracas as you have in the coastal areas, though. The coastal areas were absolutely devastated, again, because of the nature of the soil deposits there. The soil deposits are on the order of around 500 feet thick over the bedrock. And these relatively loose or soft sediments, unconsolidated as they're called, can shake like a bowl of jelly. It's just like taking a bowl of jelly with your hands and sliding it back and forth rapidly across the top of a table. And that soft or loose sediments can amplify the effects of the earthquake to produce much higher levels of ground shaking, which unfortunately is what they experienced from this Venezuela earthquake. And this area of the coast of Venezuela is no stranger to utter devastation. In 1999, a series of rainfall events produced massive debris flows. This was in December 1999. You had an initial rainfall event that produced 8 inches of rain, followed by another rainfall event that produced 36 inches of rain in a matter of 3 days, which produced these massive debris flows on the order of 10 to 15 feet thick sediment that covered this coastal area of Venezuela. And of course, the many buildings that were rebuilt on this area, but more importantly, this has happened for thousands and thousands of years to produce, as I mentioned, about 500 feet thickness of loose or soft alluvial sediment. Very poor type of material to place a multi-story reinforced concrete building on. And from this photo, this is in 1999 in the aftermath of those debris flows in La Guaira. Also, this occurred in the nearby town of Carabayeda, and this town suffered massive earthquake damage as well. And this is just a picture of a typical alluvial fan where you have water transported sediment from the mountains and deposited in a fan-like pattern. This is in the Pyrenees of France. This is a picture of La Guaira pre-earthquake. So as I mentioned when I recently did a video about the Philippine earthquake that occurred last month, there are several key factors usually involved with producing widespread earthquake damage. The first is poor quality materials or workmanship. Another is inadequate design methodologies. Another is inadequate codes or inadequate code enforcement. Apparently, in Venezuela, they didn't start taking the idea of seismic risks to their buildings seriously until the mid-'80s. And apparently, their codes now are quite up to date. But again, it's a question of when these buildings were built. I think, obviously, efforts need to still focus on rescue, although I think that window may have unfortunately closed, and now focus on recovery effort. But certainly, there needs to be teams of engineers and scientists going in these areas, and a lot can be learned. For example, are most of the buildings that collapsed related to their age of construction, which would indicate typically code issues? Venezuela has been a poor country for many decades, even though they're very oil rich. And I'm not going to get to the geopolitical aspects of it, but ideally, you would have more buildings that were constructed of structural steel, which have much better performance in major earthquakes than a reinforced concrete structure. Although reinforced concrete structures can be built successfully in high seismic areas, again, depending on when these were built, they could have been built well before these codes were updated. Improving the seismic performance with buildings is an ongoing effort. Japan has the largest, what they call shake table in the world, and you can build scale models of buildings, many times even half scale buildings. You can see this is a reinforced concrete building model, and the shake table simulates ground acceleration from a major earthquake. And they can put strain gauges and accelerometers and, of course, photograph the performance of these elements in the building subject to shaking and learn a lot. So they go to this kind of expense and effort to continually update international building codes for seismic performance. And apparently this earthquake or set of earthquakes in Venezuela produced ground shaking on the order of 2 to 3 minutes, which is just utterly devastating. And it's the shear waves, the S waves, that do the most damage. They produce the most ground shaking. The initial jolt from the compression wave typically travels through the Earth's crust at a speed of around 5 miles per second. And the S waves is about 60% of that, so roughly 2.5 miles per second. But it's the S wave that does the damage in these situations. The largest shake table in the United States is at the University of California, San Diego. This is a half-size scale model of a reinforced concrete building, 4-story building. So I mentioned that the nature of the soil deposits in these coastal areas of Venezuela contributed to amplification of the ground motion, as similar to shaking a bowl of jelly. And why this is so damaging to buildings is because of what's called the P delta effect. when you have shifting of the building columns from horizontal ground acceleration, you generate an excess moment in the building columns. So instead of having the gravity loads of the building and the live loads acting in a straight vertical line through the main structural members of the building, you get this offset loading now where there's a twisting or a moment that can cause those members to rupture. And we see this with this Japan video where these structural members are breaking, and designers and code officials can use that information to change the nature of the detailing for these structural members. They could figure out where shear walls need to go. That happened after the 1994 Northridge earthquake in California. I happened to be there a few days after that earthquake, and there were several parking garages that had collapsed or were near collapse, and they realized that many of these buildings needed improved shear wall reinforcement. So I suspect that's what happened in many of the instances of these collapsed buildings in Venezuela, is that there was inadequate shear reinforcement, basically to make the columns more rigid or more better supported for lateral loading. And then, of course, you've got also concerns about connection details from the floor slab to these building columns. But whenever you see a building that collapses in a heap, obviously that's a catastrophic failure of a building, and it's most likely related to these P delta effects for the building columns or the building column floor slab connections. So I'll continue to follow this story and provide updates. With that, I want to send a shout out to those of you who've contributed to buy me a coffee. That's one of the better ways to support this channel. I also want to thank the channel members and those of you who've contributed to Sewer Things. Thanks very much, everyone.